The title talk is Video Representation Learning through Prediction for Online Object Detection. I'm Fujitake. This is joint work with Akihiro Sugimoto. Video object detection is the task of identifying the object position and levels in the videos. It has received increasing attention as it sees immense potential in real-world applications such as robotics, surveillance camera, and smartphone. However, compared to still images, it is more challenging due to the motion blur, occlusion, and autofocus and so on. To deal with these challenges, some offline algorithms utilize feature aggregation from the past to the future frame. It is more effective to boost detection accuracy. However, online video object detection methods cannot rely on these advantages or future information. Therefore, in the last few years, object detection methods for live streaming video have been proposed to tackle these problems. There are two main categories. One is propagation-based approach, generating a robust feature map by propagating the information from the past to the current frame. On the other hand, prediction-based approach have been proposed recently. It does not only propagate past information, but also run time series information to predict the futures. It is more effective than existing propagation approach because it requires more active learning of information such as object motion to predict future state. However, proposed method does not fully utilize future information because it only exploits short term, the next frame. Therefore, the motivation of our research is to use longer-term future information to enhance the features. However, long-term prediction is difficult due to the uncertainty of futures. A deterministic model outputs an average of futures. This is not a problem for short-term futures, but it is challenging to optimize for long-term prediction because it simultaneously depicts multiple possible futures. Therefore, we propose a method to obtain a video representation based on the stochastic future prediction to utilize long-term future forecast and use it for object detection. Since stochastic future prediction is difficult to learn, we propose two-stage methods. First, we train our model only stochastic future forecast in advance. Then, we fine-tune the model to the detection task. The novelty of our research is object detection methods through stochastic future prediction and the two-stage training method based on the pre-training and fine-tuning. Our method is based on stochastic adversarial video prediction called SAVP, combining VAE and GAN. VAE stochastically samples the future possibilities, and GAN optimizes the generated future frame to be close to the real one. SAVP takes the current frame as an input and generates the image for next frames. However, for object detection, we need to output the current frame detection results. Therefore, for the same time input, we need to produce output for different time steps, one for the present and one for the future. We also need to perform object detection and image generation. To achieve these tasks, we propose a modules, encoder, decoder, and synthetic heads. The recurrent encoder stores time series information. The recurrent decoder generates the future at different time steps based on the encoder output. The synthetic head generates the frames based on the features from the decoder. For pre-training, first, encoder is initialized using the past frame. Then, using the current frame as input, it reconstructs current frame like autoencoder. It then takes the latent variables and updates the decoder time step to generate next frame images. This process is repeated from T frame to generate the future frame. Finally, the generated frames are optimized by GAN. The next is fine-tuning the model for detection. To perform detection, a detection head is attached to the output of the decoder. In the fine-tuning, object detection is trained using the weights obtained by pre-training. We trained both detection and future prediction in this phase. The novelty is fusion of stochastic future prediction and video object detection. We also propose two-step training method for video object detection. In the inference step, all modules except for detection are removed because there is no need for future prediction. It detects objects as same as the typical video object detectors. The architecture for current frames looks like this. The encoder and decoder are based on a resonant FPN, and convolutional RSTM is attached to the output of each block. Detection is conducted from the output of the decoders, and frame reconstruction is done from the output of P3. The architecture for generating future frames looks like this. First, the latent variables are sampled and encoded through the LSTM. Then, they are added to the lateral connection between the encoder and decoder channel wisely to generate future frames. We perform validation on large video datasets, the ImageNet VID. It consists of 30 categories with about 4,000 training and 500 validation videos. The detection accuracy is evaluated by the mean average precision. We use ResNet and F-cross detectors. As a pre-training, we train a future prediction in a 10 epoch. Then we fine-tune to the detection in 5 epoch. First, we compare our method with real-time and online video object detection method. In terms of accuracy and speed, the proposed method achieves the best performance. Using the same backbone, our method is faster and stronger than the latest method. This is visualization result. We see that it detects robustly. In order to validate the effectiveness of our methods, we perform a component analysis. In this experiment, all training epochs are the same. Our methods improve the detection accuracy by 4.4% from the baseline. Without pre-training, accuracy decreases, indicating that it is better to train only the future prediction in advance. Next, the method accuracy without prediction decreases, indicating a simple recurrent neural network is not sufficient. Pre-training requires only video frames and does not utilize any annotations. By dividing the training process into two stages, pre-training and fine-tuning, we can use any videos in the pre-training phase. For this reason, we conducted experiments changing the pre-training data to other videos and using the ImageNet VID dataset in the fine-tuning step. We use YouTube VB dataset whose scene is similar to ImageNet VID, and BDD100K, a driving scene dataset, replacing the ImageNet VID to YouTube VB. The accuracy increased by 3.5 points. Surprisingly, we found that BDD100K with completely different scene also increased their accuracy by 2.1. Since making annotation is costly, the accuracy improvement without annotation will be great contribution in real-world application. Here is conclusion. The purpose of this research is to realize high accuracy online video object detectors. To achieve this, we propose a video object detection framework combining stochastic feature prediction. We also propose a two-stage training method. First, in the pre-training, we learn video representation through feature prediction. Then, we transfer the model to the detection task in the fine-tuning step. As a result, our model outperforms existing methods. We also show that accuracy improvement by replacing the pre-training data with large number of unlabeled videos. We hope it could be beneficial for real-world applications. Thank you for listening.